Okay, and the last segment for this lecture is about total correctness. So far we've only been concerned with partial correctness, and total correctness means partial correctness plus normal termination, right? So no looping, no other form of divergence, no runtime exceptions, division by zero, whatever. So of course for our while language, we have none of this. So the only bad thing that can happen is that we don't terminate somehow. And in fact, that would happen because of a loop, so that we end up in infinite loop. So now the syntax is a bit different. We're using these square brackets instead of the curly braces. And the meaning is if P holds before S is executed, then the execution terminates normally. And Q holds in the final state, right? So suddenly it's not if it terminates normally, but it does terminate normally and, right? So that changes everything. And then if the programs are deterministic, just like our while programs, we can reformulate it like this. We can say if P holds before S is executed, there exists a state in which execution terminates normally and Q holds in that state. Because it's enough to have one state, because there cannot be more than one. So if you have one, then you have all, and therefore you're fine. And here's a concrete example. So if I is less than 100, and you have the same loop as before that you recognize, then you have that I equals 100 afterwards. But you see, you absolutely need this precondition. You cannot say true here. That wouldn't be correct, because this program can diverge, right? So this is the best we can say using total correctness about this program. So right. So how can we achieve that with how can we achieve total correctness in practice in hoare logic? Well, the trick is to add the notion of variant, right? So we want to prevent infinite loops. So we have to basically we'll require the users, whenever they specify a loop, we'll require them to specify a variant, which is a kind of bound, on the number of iterations that the loop will take. And they will have to show that each iteration of the loop decreases the variant. And that way we'll be able to establish the hoare logic triple for total termination. So what would be the variant for this example above? And it's a pity, there are no students to answer. I remember last year the first answer was wrong, so it makes people think. This time I will give the first answer. Let me think, and maybe it's going to be wrong, like 5 + 5 equals 25. Let's see. So the variant here is something that decreases with each call. So it would be maybe 100 minus I, right? So right, because your I increases, so you want to write minus I so that it decreases, but you don't want to go into negatives either. It has to be a natural number. That's the whole point. It has to strictly decrease, I should say. It's really strict. But so that means 100 minus I should be fine. Okay. So I think there's a bit more about this topic in the Hitchhiker's Guide. We're not going to insist much on total correctness. It's just, it's a nice concept to know about, and it's the, it's the gold standard of theorem proving. But, for the purposes of this course, I think we have enough to do just playing mostly with the partial correctness. Although it's possible that total correctness reappears in some of the exercises or homeworks. All right, so this completes hoare logic, and which is a second out of 3 semantics. And in the next lecture, we're going to see the denotational semantics.